Hi there! It's time to get into the design and realization of the elements that make up the Theremin V.2 volume control. Today we will start by examining the low-pass filter, and we will see how it will help us to get a good sensitivity in controlling the volume of the theremin. Before diving into the details, please take a moment to subscribe to this channel and click on the bell icon to receive notifications when new videos become available. The subscription will also help in making the channel grow and serve you better. And now, let's begin. Here is the schematic of our filter. It is a relatively simple circuit made out of a single op-amp and a few resistors and capacitors that provide the whole topology of the third-order Sallen-Key low-pass filter. The topology of this filter is based on the topology of the simple first-order low-pass filter, repeated 3 times to obtain the third-order capability. Let's see in more details how this is done. We start with the simplest form of low-pass filter made up of 1 resistor and 1 capacitor. This is a first-order passive low-pass filter. With a DC input, the capacitor obviously is basically an open circuit, and the output signal is identical to the input signal. With an AC source, the capacitor starts presenting a reactance, which is the equivalent of the resistance for the capacitor. The higher the frequency, the lower is the reactance, and therefore the output signal, which is the signal across the capacitor, becomes lower and lower. If we represent this behavior on a semi-log diagram, the frequency on the x-axis and the output signal amplitude on the y-axis, we obtain this kind of curve. By the way, this curve is called the Bode Diagram for the magnitude. The cutoff frequency of this filter, or the frequency at which the attenuation of the signal is -3 dB, is given by this formula: Fc equals 1 over 2 pi Rc. So, in other words, this is the frequency at which the output signal has at 70.7% of the amplitude of the input signal, or 1 over square root of 2. Let's now look at the corresponding first-order active low-pass filter. The response diagram of such a filter is still the same as the passive one, and so it is the cutoff frequency formula. However, the output of such a circuit has a very low impedance, and we can safely draw current from it without changing the response of the filter, which wasn't possible in the case of the passive filter. The next step is now to put together 2 low-pass filters to obtain a second-order low-pass filter. You can see it in this picture and see how R1 and C1, along with the op-amp, have the same configuration as the first-order active filter we have seen in the previous picture. Now, however, we have an extra passive low-pass filter made of R2 and C2, connected just before the non-inverting input of the op-amp, and this provides a second level of attenuation of the signal. This filter is able to attenuate the input signal twice as fast as the first-order filter, as you can see by the increased slope of the Bode diagram. The cutoff frequency is now calculated with a new formula, which is this one: Fc equals 1 over 2 pi square root of R1, R2, C1 and C2. This filter topology was invented in 1955 at the MIT Lincoln Laboratory by R.P. Sallen and E.L. Key, and has been named after them ever since. The next step to obtain the third-order filter is to add one last low-pass filter stage to the schematic, which now resembles the previous schematic but with the addition of R3 and C3. Notice how the slope of the Bode diagram has increased even further, and this is the effect of having 3 low-pass filters acting in concert on the signal. Now that you have a better understanding of the filter theory, let's go back to the schematic of our filter for the theremin, and let's take a look at its magnitude Bode diagram. We can see that the region where we want to use this filter to achieve a good ratio between amplitude and frequency variations, while keeping the signal at a reasonable amplitude, is around 250-300 kHz, just about the cutoff frequency. When the signal coming from the volume variable oscillator changes in this interval, we can catch it in this region of the filter, and then we can take the amplitude of the output signal to drive the voltage controller attenuator. This should work much better than the circuit used in the previous design, the old Theremin V.1 from last year. Let's now take a look at how this filter behaves in a lab test. I mounted the low-pass filter on this breadboard, where I'm also working on the other blocks of the volume control unit, which I will present in separate videos. You can see here the op-amp around which the rest of the filter is built. The power supply comes at pins 7 and 4, where it is also filtered by a couple of capacitors. These other capacitors are those relevant for the filter C7, C8 and C9 in the schematic. You also see here 5 resistors instead of 3. That's because I needed specific values for a couple of them that do not exist in the standard decades, so I had to make them combining a couple of resistors. The input signal for the filter test comes at resistors R4 to which the red alligator is connected. Here is the function generator I used to inject the signal into the filter. An oscilloscope probe is connected to the output of the filter on pin 6 of the IC. It goes to channel 2 of the oscilloscope, the one that is visualized in blue. Channel 1 of the oscilloscope in yellow is connected directly to the function generator, so we can see both input and output waves at the same time and compare them. And here are the signals on the oscilloscope monitor. Right now, I am generating a frequency of 10 kHz, too low to be attenuated by the filter, so the two signals are basically identical. You can also see that increasing the frequency up to 50 kHz doesn't change the output, since we are still far away from the cutoff frequency. And again, at 100 kHz there is no change on the level of the output signal. But now look at this. At about 150 kHz we start noticing a change in the level of the signal. Just a little bit right now, since we are still below the cutoff frequency. Increasing the signal frequency even further, we can now see how the amplitude of the signal starts to decrease noticeably. You see how the blue wave is now smaller in amplitude than the yellow one? And of course, going even higher in the frequency, the signal amplitude keeps getting smaller and smaller. And now, at about 300 kHz, the output signal has an amplitude about half the size as the original input signal. And the farther we go with this frequency, the smaller becomes the amplitude of the output signal. Of course, when we decrease the frequency, the signal amplitude increases again. Let's now build the Bode diagram for the magnitude by measuring the amplitudes for given frequencies. This way, we can make sure that the real filter works in the same range as the theoretical calculations. I already prepared a semi-log blank paper by writing down the frequencies and amplitude in the ranges we are going to take the measurements. Frequencies are on the x-axis, which has a logarithmic scale, and amplitudes on the y-axis, which has a linear scale. So now, let's take the first pair of measurements, 10 kHz and 8.56 volt, and let's mark the corresponding point on the diagram. Now let's do the same with the second pair, 30 kHz and 8.56 volts. The third pair, 50 kHz and 8.56 volts. So far no change in the voltage. The fourth pair, 70 kHz and 8.40 volts. You see, now we can see a little diminishing of the amplitude. Here's the fifth pair, 100 kHz and 8.32 volts. The sixth pair, 150 kHz and 7.52 volts. The seventh pair at 100 kHz and 6.32 volts. And finally the eighth pair at 250 kHz and 4.80 volts. This is all we need for our diagram. So let's now connect the dots and see what we got. And there we go. It looks like just the theoretical diagram, you see? Now all we need to do is to connect this filter to the other blocks of the volume control unit and make everything work together. We will go through all of this in the next few episodes of the Theremin projects, and you will see how this will evolve. In this video we went through the description of the low-pass filter used in the Theremin V.2. I also took the opportunity to go a little deeper in describing why the filter was historically designed this way, and finally I showed both the theoretical Bode diagram and the one captured on the real filter in the lab. The diagram helped us to understand why we are using such a filter in the volume control of this new Theremin. The next video on the Theremin will be concentrated on the peak detector, another interesting piece of this totally new design. In there, we will see how the peak detector can determine the amplitude of the signal coming out of the low-pass filter. Thank you for watching this video, and don't forget to give it a thumb up, which will greatly help improve its visibility so others can enjoy it too. Also, if you have not subscribed to the channel yet, please do so now to help making more and better videos. Talking about help, a small monetary contribution can help too. There are a couple of options you can choose from: Patreon and PayPal, both listed in the video description below. See you in the next video, and as usual, happy experiments!